In today's lecture, we'll look at some applications of different exponential and logarithmic models. We'll look at two in this lecture, and these are sort of the most important ones. They're definitely the ones that come up the most. They're functions for exponential growth and exponential decay. Now notice here that they both have this requirement b is greater than 0. And that's because for exponential decay, we have this negative already assumed to be in the function. So if we're getting larger, then we have this variable a and b that we need to find out. And if we're getting smaller and we're decaying, then we have a and negative b. And these variables here are normally what needs to be solved when we look at these equations. Or they're possibly given to us and we just need to plug in x and y values to see what we get as an outcome. So while these functions are simple, they're very powerful, and let's look at three examples of different kinds of exponential growth and exponential decay. Our first model talks about online advertising. And notice here that the dollar amount is in billions. So we have a chart, and it shows how many years have gone by, starting from 2011 to 2015, and how much a company has spent on advertising in billions. So in 2011, they spent $31.3 billion. In 2015, they spent $49.5 billion. And by looking at this, we can turn this into an exponential equation that's modeled by s is equal to 9.3. So this is our a here, times e to the power 0.1129, which is our b, times t, where t is our years. And this works if t is between 11 and 15. If we plug in 11, this corresponds to the data for 2011. If we plug in 15, it's 2015. Now this isn't a perfect match. If we look at the model below, we see that by plugging in 11 to our function, we get 32.2, and the real answer is 31.3. But it matches up pretty nicely, especially later on in the years. We see in 2014 the actual amount spent was 45.5, whereas the model gives us 45.2, which is rather close. And similarly, we have 49.5 for 2015, whereas the model gives 50.6, so it's just about one away. So with this model, we can plug in values that are larger than 15 in order to see how much money we want to spend in the future. Or we can answer the question, at what year can we expect to spend $80 billion? So we can look into the future and get an approximate year we expect to spend $80 billion in online advertising. So let's set this up in our function. We want our output to be 80. And remember, this represents 80 billion here. Our a and our b have already been found. So this is 9.3 times e to the 0.1129 times t. And we want to solve for t, since t represents the years. Using our exponential equations, this is rather easy to solve for. You just might need a calculator to make some approximations. Okay, so the first thing we want to do is get rid of the 9.3. So we divide that to the other side. And we have 80 divided by 9.30 is equal to e to the 0.1129 times t. And now that only the exponential is left, we can move this base of our logarithm to the other side, and we'll get ln of 80 divided by 9.3 is equal to 0.1129 times t. Since our exponential on the right-hand side had base e, then when we move it to the other side, our log has base e as well, and it's a natural log. To finish this off, all we need to do is divide the 0.1129 to the other side, and we'll have that t is equal to the natural log of 80 divided by 9.3 divided by 0.1129, which is approximately 19.1. This means that in the year 2019, we can expect to pay 80 billion in advertising. And we've answered the question. So when we have the basic rules down for exponential equations and logarithmic equations, it's about as easy as adding or subtracting or multiplying or dividing. All right, so now let's look at another example here, and we'll model some population growth. And again, we see that this is growing according to the law of exponential growth. So this means we need to set up some function. Y is equal to a times e to the bx. And if we look, they give us inputs and outputs right away, and we need to solve for a and b. Okay, so let's see what we can say here. After 2 days, there are 100 flies. So that means that our output of flies is 100. When we plug in 2 for x, and similarly, after 4 days, there are 300 flies. So we output 300 flies when we input 4 days. And with these two equations, we have everything we need to solve for a and b. We'll have to do a bit of a substitution here. So let's first solve for a, and then make a substitution into the second equation, and we'll have our answer. So we'll start here, and we want to get a by itself, and that's easy. We'll just pretend e to the 2b is a number, and divide it to the other side. Now we have a is equal to 100 over e to the 2b. And once we know what b is, we've solved this. But for now, we'll come back to it later. Our next goal is to take this number, a is equal to 100 to e to the 2b, and plug that into the other equation and see if things simplify. So equation 2 says 300 times a, but instead of a, it's 100 divided by e to the 2b, times e to the 4b, should be 300. And if we combine top and bottom here, we have 100 e to the 4b divided by e to the 2b, should be 300. And now we can cancel things on top and bottom. We have 4b on top and 2b on bottom. So this cancels out and leaves us with 100 times e to the 2b. And this is because 4b minus 2b is 2b. We've gotten rid of a from the equation here, so if we can solve for b, we'll be done, and then we can solve back in and find what a is. And we can solve for b if we simply use our rules for solving exponential equations. First, we divide 100 on the other side, and we have 3 is equal to e to the 2b. Next, we want to move this e to the other side, so it crosses over and becomes a logarithm with base e. So natural log of 3 is equal to 2b. And then finally, b is the natural log of 3 divided by 2, which is actually the natural log of the square root of 3, which is simply 0.5493. And we've solved half of the equation here. B has a nice numerical value for it now, 0.5493. Now we'll plug it in back up here and solve for a and be done. A is equal to 100 divided by e to the power 0.5493. And with a little help from our calculator, we get that a is approximately 33.33. Okay. So now that we have this, we can finish off our equation here. Oh, and of course this is times 2. Let's rewrite y is equal to a times e to the 2b as y is equal to 33.33 times e to the power 0.5493 times x. And now we're free to plug in x values and find some y values. So if x equals 5, which corresponds to 5 days, we can find the number of flies. Okay, so y is equal to 33.33 times e to the power 0.5493 times 5. And again, everything's sort of solved, so all we have to do is plug this into a calculator, and we'll see that the answer is y is about 520 flies. So after 5 days, we can expect 520 flies. And we were able to solve this by just having 2 data points, that after 2 days, there were 100 flies, and after 4 days, there were 300 flies. Then we solved for a and b, and simply could plug in any x value we wanted to find the number of flies after so many days. All right, let's look at the third example here. So this example looks at carbon dating. We need to know a little bit about carbon dating to make this work. So in living organic material, the ratio of carbon-14 to carbon-12 is about 1 to 10 to the power 12. So for every carbon-14 we have 10 to the power 12 carbon-12. However, when an organic material dies, the carbon-12 remains fixed, but the radioactive carbon-14 begins to decay with a half-life of 5,700 years. So the word decay here tells us we're going to be using exponential decay. The ratio of dead organic material is modeled by the equation R is equal to 1 divided by 10 to the power 12 times e to the power negative t divided by 8,223. And R is the ratio here. So with this equation, if we can plug in some R values, we can find t by back solving, and we can find the age of the fossil if we have a nice ratio of carbon-14 to carbon-12. So for this example, it's given to us that we have some fossil with a ratio of carbon-14 to carbon-12 that is 1 divided by 10 to the 13th. And we'll use this now to approximate the age of the fossil. So our ratio is 1 over 10 to the 13th. And this ratio is equal to 1 over 10 to the 12th times e to the negative t divided by 8,223. And in order to solve this, all we need to do is start moving things to the other side, add in a logarithm, and solve for t. So the first thing we'll do is we'll multiply by 10 to the 12th to the other side, and we get 10 to the power 12 divided by 10 to the power 13, which cancels out and is just 1 over 10. is equal to e to the negative t divided by 8,223. Now, the e is by itself, so we can move it to the other side and make it a logarithm. And we have natural log of 1 over 10 is equal to negative t divided by 8,223. And to solve for t, all we need to do is multiply by negative 8,223 to the other side. So t is equal to negative 8,223 times the natural log of 1 over 10. And again, with our calculator, we get this is about 18,934. So the fossil is about 18,934 years old. And we've done it. Now, these aren't the only examples of where we see exponential and logarithmic equations. They appear quite often in nature, and they actually appear quite often in business as well. So in the next lecture, we'll look at 3 more examples and where they might arise when we're looking in the natural and the business world.